Welcome to the Deep Dive.
Great to be here.
Today we're tackling a big one, quantum computing. Sounds really sci-fi, right?
It does, but the thing is, it's moving so incredibly fast. What seemed like science fiction is, well, becoming today's news.
Exactly. We've been digging into some material that gives a snapshot of where things stand, like right now in 2025.
Yeah, and it highlights some pretty significant breakthroughs that are happening as we speak.
So our mission really is to unpack this. What is quantum computing? Why all the buzz? And, what do these latest developments actually mean?
And there's one big piece of news the sources focus on, this new chip from Microsoft. Sounds potentially game-changing.
Okay, let's dive in then. For someone maybe just starting to get their head around this, what's the fundamental difference? How is quantum computing not just like a faster version of my laptop?
That's the key question. At its core, it's using the weird rules of quantum mechanics, the physics of the super small, to actually compute things.
Okay.
So your laptop uses bits, 0 or 1, off or on.
Like a light switch, yeah.
Simple.
Right. Quantum computers use qubits, and this is where it gets different because of something called superposition.
Superposition. Okay.
A qubit isn't stuck at just 0 or 1. It can be 0, it can be 1, or, and this is the crucial part, it can be a sort of blend of both at the same time.
Like the spinning coin idea. While it's spinning, it's not heads or tails yet. It's kind of potentially both.
That's a really common analogy, yeah. It captures that idea of holding multiple possibilities at once. Before you measure it, it exists in this state of potential.
And that lets it, do more calculations?
It lets the computer explore a vast number of possibilities simultaneously. Instead of checking answers one by one like a classical computer often does.
It can look at loads of them all at once.
Exactly.
Yeah.
Exponentially more for certain problems. So superposition is one pillar.
Got it. What's the other quantum trick?
The other really strange and powerful one is entanglement.
Ah, yes, entanglement. You can link 2 or more qubits together in this special quantum way. When they're entangled, they're connected. What happens to one instantly affects the other.
Instantly. Even if they're miles apart, that's the spooky part, right?
That's the spooky action at a distance Einstein talked about, like those magic dice you mentioned. If one lands 6, the other instantly does too, no matter what.
Okay, that's weird. But how does that help computing?
It creates this incredibly powerful correlation. The qubits can work together in concert, processing information in complex ways that classical bits just can't. It's key to the speed up for certain calculations.
Fascinating stuff.
Yeah.
But this isn't totally new, is it? Where did the idea even start?
Well, the theory goes back a ways,
Yeah.
mostly the 1980s. People like Richard Feynman, David Deutsch, they realized that trying to simulate quantum systems, like how molecules behave on classical computers, was just incredibly hard. Basically impossible for complex stuff.
So you needed a quantum machine to simulate quantum things.
Pretty much. That was the initial spark. Build a computer using quantum mechanics to understand quantum mechanics.
And then Peter Shor came along in the 90s, and suddenly it wasn't just for physicists anymore.
Exactly. Shor's algorithm was a bombshell. He showed mathematically that a quantum computer could factor really large numbers super quickly.
Which sounds technical, but is a massive deal
Because modern encryption, the stuff protecting your bank account online, your emails, everything relies on the fact that factoring large numbers is hard for classical computers.
Right.
Shor showed a quantum computer could potentially break that encryption wide open. That's when people really sat up and took notice of the power and, frankly, the potential danger.
Okay, so if classical computers are like trying one path in a maze at a time, maybe a few, quantum computers with superposition and entanglement can somehow explore all the paths at once.
That's a decent way to think about the potential advantage for specific problems, yeah. But, and this is huge, but building these things is incredibly difficult.
Why? What's the catch?
The qubits themselves, they are unbelievably delicate, fragile. Any tiny disturbance from the outside world, a vibration, a change in temperature, stray magnetic fields, just noise can knock them out of their quantum state. It's called decoherence.
And when that happens, errors.
Exactly. You get errors in the calculation. And fixing errors in a quantum computer is way harder than in a classical one. It's been the fundamental roadblock for decades.
Which, I guess, brings us right up to the present day. And the big news our sources are highlighting from 2025, this fragility problem. That's what the breakthroughs are targeting.
Precisely. The headline news in the material we looked at is about Microsoft's new chip. They're calling it Majorana 1.
Majorana 1. Okay, what's so special about this chip?
The sources say it's all about stability. They're using a completely new type of material that seems to allow them to create qubits that are just inherently more stable, more reliable.
So the building blocks themselves are tougher, like using stronger bricks.
Kind of, yeah. And this new material lets them build what are called topological qubits. That's the real innovation here, according to the source.
Topological qubits. How are they different?
Well, unlike regular qubits, which are super exposed and easily disturbed, these topological ones are designed so their quantum information is sort of smeared out, protected by the structure itself.
Ah, like that shield analogy. Built-in protection.
Exactly. It makes them naturally much more resistant to local noise and disturbances. The upshot is they make far fewer mistakes.
Fewer mistakes. That sounds huge. Because error correction is so hard.
It simplifies the error correction challenge dramatically. If your basic components are already much less error-prone, the whole system becomes more feasible.
That really does feel like it could shift things.
It could. Microsoft's ambition, mentioned in the source, is apparently to scale this towards, eventually, maybe 1 million of these protected qubits.
1 million? Wow.
And they're working with the U.S. government, DARPA, on a program called US2QC. The goal there is specifically to build a test machine using these qubits that can essentially fix its own errors intrinsically.
So, tough qubits that can also self-correct.
That's the dream. And the sources suggest that if this topological approach works out, it could really speed things up. Practical quantum computers might be years away, not decades.
That's a pretty dramatic acceleration. But Microsoft isn't alone in this race, right?
Oh, definitely not. The material also pointed out IBM's progress. They've got a new 156 qubit chip.
Okay.
And the notable thing there is, for certain specific calculations, it's apparently 50 times faster than their previous generation chip.
50 times faster in one go.
Sure.
That's rapid improvement.
It shows how quickly things can move, yeah. And Amazon has mentioned, too, they've also developed their own quantum chip now.
Those are heating up.
Yeah, and the sources frame this competition as a good thing. Multiple big players, different approaches. It pushes everyone faster toward actually building something useful.
Right. Okay. So we're seeing progress on making qubits more stable, faster, getting more of them. Let's get to the so what? Why should we care? What could this actually do?
Well, this is where the potential gets really exciting, based on what the sources lay out. Quantum computers promise to solve problems that are just impossible for today's best supercomputers.
Like what kind of problems? Give me some examples.
Okay, materials science. Think about designing new materials. To do it really well, you need to simulate how atoms and molecules behave at a quantum level.
Which classical computers struggle with?
Massively. Quantum computers could model these interactions accurately. Imagine designing super efficient solar cells, better catalysts for green hydrogen, maybe even self-healing concrete. Things like that.
Inventing entirely new stuff based on understanding it at the quantum level.
Yeah, okay. What else? Medicine. Drug discovery is another huge one. Figuring out how a potential drug molecule will interact with proteins in your body is incredibly complex.
Takes ages now, right?
Exactly. Quantum computers could potentially simulate these interactions much, much faster, speeding up the design of new drugs, personalized medicines. It could revolutionize healthcare.
That would be incredible. And we mentioned cybersecurity earlier, the dark side and the light.
Yeah, it cuts both ways. Quantum computers threaten today's encryption, the stuff based on factoring, like we said.
Right, Shor's algorithm.
But quantum mechanics also offers the tools for new kinds of encryption, quantum key distribution, things that are theoretically unhackable based on physics principles.
So it creates the problem and the solution.
In a way, yes. It forces a move to new security standards. Then there's AI.
Ah, artificial intelligence. How does quantum fit there?
Some quantum algorithms could help AI systems learn or find patterns in data much more efficiently. Exploring possibilities faster could lead to smarter AI for really complex jobs. Climate modeling, optimizing power grids, maybe even more advanced medical diagnostics.
So making AI even more powerful. What about, like, everyday business stuff?
Yeah, business optimization. Think about incredibly complex logistics, optimizing delivery routes for a huge fleet of trucks globally.
Nightmare problem.
Totally. Or managing financial portfolios, analyzing risk with many interacting factors. Quantum computers could potentially find optimal solutions to these kinds of problems that are just too big and complex right now. Saving time, saving money, making better decisions.
Okay, it really feels like this could touch almost everything eventually. But let's be realistic. Despite the Majorana 1 excitement, the sources were clear we're not quite there yet. What are the big roadblocks still?
Oh, absolutely. The challenges are still massive, even with breakthroughs.
Like building enough qubits, is that the main thing?
That's probably the biggest one,
Yeah.
scaling up. Going from, say, 100 or even 1,000 qubits to the millions likely needed for truly fault-tolerant, powerful quantum computing. That's an enormous engineering challenge.
Millions.
And even if topological qubits are more stable, they aren't perfect. You still need error correction. Managing errors across millions of interconnected, sensitive quantum components reliably. That's still a huge research area. It needs better materials, better designs, better control systems.
So even with better parts, assembling the giant perfect machine is the hard part.
It's incredibly hard. And then there's the software side.
Right, you need programs to run on it.
Exactly. You can have the most powerful quantum hardware in the world, but if you don't have the algorithms and software that know how to actually use that quantum power effectively to solve real problems...
It's just an expensive paperweight, like having a Formula One engine without a car or a driver.
That's a good analogy from the source, yeah. Powerful engine, but you need the skilled driver and the right kind of racetrack. Developing those quantum algorithms is a whole field in itself.
And presumably you need people who understand all this stuff.
Definitely. We need way more trained experts, physicists, engineers, computer scientists who get quantum. And the field needs standards, ways to compare machines, ways for people to collaborate effectively. Lots of groundwork still.
Okay. So, wrapping up this deep dive, we've gone from the basics, the weirdness of qubits and entanglement, to seeing how specific breakthroughs, like Microsoft's Majorana 1 chip, using these topological qubits, are trying to tackle those fundamental problems of stability and errors.
And seeing progress from IBM on speed, Amazon jumping in, it really shows the momentum building.
Yeah, and we've looked at the sheer potential across so many fields: materials, medicine, AI, finance. It's kind of mind-boggling.
It really is amazing to see it shifting, from pure theory towards something that might actually be practical.
And even acknowledging those big hurdles, scaling, errors, software, the pace of change feels intense right now. This competition seems to be pushing things forward really fast.
It definitely feels like we're on the edge of something potentially transformative, even if the exact timeline is fuzzy.
It really makes you think, doesn't it? How fast this has gone from a concept in physics labs to something that major companies are pouring billions into, something that could genuinely reshape industries. Maybe sooner than we thought. Based on everything we've discussed from the sources today, where do you think we might see the first really big, tangible impact? Will it be designing a new wonder material, cracking drug discovery, or maybe something completely different breaking through first? Definitely something to keep an eye on.
For sure. Lots to watch.
Thank you for joining us for this deep dive.